So are there any questions?
Or Alaska.
Philip Boyd, Australia.
Where are you, Phil?
Oh, sorry, here in the corner.
Okay,
Down a mine shaft in the corner.
Yeah.
So, I suppose one of the big developments that's happened over the last decade or so has been a really big appreciation of mesoscale variability, and now with work by people like Marina Levy, the sub-mesoscale variability. And I suppose one of the things that we probably have to ask ourselves is that in many cases, people who focus on this, they go to these natural laboratories, such as Kerguelen, where there's a real shredder going on and you get fantastic gradients. But then, if you look across the rest of the ocean, what actually happens when we look at the main field? Do these things actually start to average themselves out? Because it's a very important question, because if we really have to dive into that sub-mesoscale detail, not just as the surface, and as Adrian Martin pointed out this morning, but also, going down, then that's really going to define the level of detail and how much money we're going to have to spend. Whereas if some of those things in some regions start to smear out a bit more, it might make lives a bit easier. So have you considered that in any way?
Yeah, I think that was definitely one of the outcomes of the workshop, was that I focused mostly in the talk on the larger scale variability, the global patterns, but that was mostly because the exports, the exports implementation sort of involved some of the discussions about the tools and approaches to getting at some of those smaller scale features. But yeah, that's definitely one of the hot topics that was identified within that spatial and temporal category of prioritization.
Oh, and just one other thing. If you want to increase the stickiness on your Post-its, just give them nutrient stress. They're much stickier. So.
Okay, yes.
You should have known that.
Yeah.
Hi, my name is Bob Valancourt from Millersville University, and my question is for Holly concerning mixotrophy. I like to do chemotaxonomy using HPLC pigments to understand phytoplankton community composition. Can you tell me, once you get away from the coastal areas and the estuaries, like on the continental shelf and in the open ocean, what kind of pigments should we be concerned about as perhaps being compartmentalized within mixotrophs and not within free-living phytoplankton?
As a mathematical ecologist, I was given a safe word for this situation, which is the phrase, "I don't know." And I'm wondering if we have any photophysiologists in the room who could maybe make some statements to that, because in terms of pigment content, I personally am more familiar with some of the coastal organisms.
Okay,
So,
then what's the identity of some of the endosymbionts? Like you mentioned cryptophytes in Mesodynium, so I know to look for alloxanthin, which is a marker pigment for cryptophytes. But other than cryptophytes, what other endosymbionts would I expect to find in a mixotroph in the open ocean?
Again, I think I'll defer to people who are more familiar with the biology of these organisms. I'm sorry I don't have a quick answer for you.
Okay. All right, thanks.
I'm Barney Balch from Bigelow Lab, and I have a question for Holly and for Monica. Are microgels sources of nutrition for mixotrophic organisms?
Theoretically, if they contain polymers with a lot of nitrogen, they should like it.
Yeah, I would agree, and in general with that. In my talk today, I tried to draw a distinction between mixotrophs that were taking up dissolved or gel forms versus eating other living particulate matter. But it is quite common to see mixotrophic organisms and indeed many planktonic organisms taking up other forms of organic matter. And I agree that the stoichiometry of that source is going to really affect its palatability.
Also, gels are often colonized by bacteria, which would make them very, very nutritious, and they're enriched bacteria. So organisms don't have to eat each individual bacteria, but have a. So I would agree.
Thanks, everyone. So I was wondering, this is kind of tie-in from earlier this morning. So a lot of the most interesting, well, actually, I'll qualify this statement. Some of the recent work on zooplankton ecology and plankton ecology has been going towards smaller and smaller scales. So micro-defined scales and then utilizing genomics data. But within, kind of looking at within the global domain, we're still using models with 1 degree resolution, or in some cases there's been a few runs with mesoscale resolution. But that's still 10 to 60 kilometer resolution, and that gap, it seems like, is fairly big from that meter resolution to 10 to 50 kilometers. And I imagine that the dynamics in between those two scales are fairly nonlinear. So do you guys have any insights or ideas for how to resolve some of those differences in scales?
Mike Landry knows the answer to this, but I'll try. I'll try first. Well, I think the way to do that is using multiple approaches, because there are some things we can use, like acoustics, for example, where we can get at those scales, but then you have to ground truth it still with NetToes, make sure that you know what's there. I mean, there are some things like multi-frequency acoustics, or we can start to get at what some of the major attacks are, and at the scales you're talking about, that might be helpful. But again, we still have to ground truth. So, and then there are, some of these camera systems, towed camera systems can get at those scales, and I think the technology is getting to the point now where it's automated enough that we can know, densities of at least major attacks at those scales. So, Mike says okay.
That answer was good enough for me. But I think it depends on the question that you probably want to ask, and whether that is something that you would devote a tremendous amount of effort to doing, would have to be defined by the context of the question that you're looking at. Yeah. And these are,
if I could
probably
just
not going to focus on that scale.
also add that I think it also requires modeling to be done on multiple scales. And I think that's the key issue, is that global models are basically have a certain set scale that they're using, particularly for the biogeochemistry. But if we can move away from global models to learn about what's happening on smaller scales and then try and scale the results of those back up again through parameterizations, we can begin to maybe include some of those nonlinearities that shift between different scales.
Susanna Neuer, Arizona State University. First of all, thank you all for this wonderful work related to the carbon pump report. It's a lot of work and putting that together, including the sticky notes. I think if I want just, I think there's a unique opportunity with Monica and Uta up there on the stage to explore a little bit deeper the differences between gels and TEP particles, which I don't think I've gotten one are real, one are I understand. I think one of your last slides, Monica, you were looking at the comparison between these, more the traditional TEP type particles and the gels. And we know the TEP are matrices for aggregates. Do the gels have that possibility, or how do they interact? Do they interact? Or are there two different classes of particles that
The
don't?
difference is in the conceptual framework that we work. TEP is operationally defined by the stain that they use to stain these particles. But gels is a physical chemical definition that is broad, and it takes into account, you saw the characteristics of the polymer, the solvent, the interactions between them, and there's a big toolbox of theory and mathematical theorems to understand the behavior of these polymers. A TEP, it has served us well in the sense that we have learned, but it doesn't have a conceptual paradigm behind. It's operationally stained particles that that only stains certain polyionic polysaccharides only. So in that sense, it's different. The thing is that TEP might be gel, but we have talked.
We have made several efforts to actually measure in the same sample both things. One of the times all the samples got frozen and other disasters happened. So it hasn't happened. But I think from the properties that we know from TEP and that we know from these microgels, we can say that both groups probably have a fair amount of overlap. You would agree with that, I think, wouldn't you?
Well,
that they're not identical, but there's probably overlap. But yeah, it's two different methods, which...
Well, but it's not only the method, it's the conceptual understanding of what is a gel and the behavior of the gel. But I think that TEP microgels, they have the gelatinous behavior, but it doesn't, because the way we have used it, it doesn't mean that it is a gel. It might be gel,
exactly. Many of the properties we know about TEP indicate that it's a gel, but it hasn't been measured like a gel.
Yeah. The thing is that TEP is measured at very low pH, and we don't know that it's aggregating polymers just by staining. But I mean, there are true particles that are those size, but there are smaller ones. Is it the effect of the pH or not? So it's something that we have talked and we should do. Yeah.
Oh, can you hear me? Thank you for the really excellent talks this afternoon. I'm coming back to my question of this morning. I asked a question about why mixotrophs were not explicitly in a compartment in that wire diagram that we saw in the exports program. And I asked this question because the idea of exports also is to look at long-term effects of climate on ecosystem that are evolving. And I've been working in the Arabian Sea for a long time, and as you know, the tropics are changing a little faster than temperate waters, and there we see a transition from ecosystems that were once dominated by diatoms to mixotrophs. And this change is happening so fast that I want to ask you whether you think it is an important box that we should add in the flow chart that was shown earlier in the morning.
Well, I think that you can guess that my answer to that question is yes, absolutely. I think there's a lot to be gained, particularly as you note, given the fact that we expect mixotrophs to play a more dominant role in many communities, not just in the oligotrophic gyres like I alluded to, but also, as you're noting, in lower latitude waters as well. And so I think that lends a sense of urgency, right, to the need to incorporate these organisms into models of various processes at various scales.
Wilf Gardner, Texas A&M University. I want to come back to the TEP and gels. Do you have any idea what the optical response is for either of those? That is, beam attenuation or light scattering, since that's an instrument that's used for looking at sort of particles.
Actually, I haven't measured, but Colleen Ressler has a paper. She doesn't call it gels, but she shows that the particles are changing and have a very similar kinetics of assemblies, and that the optical characteristics are changing. Also, there's a paper by Pace on gels from lakes, and since lakes undergo changes, a lot of changes in pH that are quite drastic, they see these gels undergo phase transition, and they see differences in the optics.
And they're sure they're purely gels as opposed to other types of particles too?
They work with Pedro Verdugo, and they measure it with laser scattering, and they are gels.
Okay.
Panelists, please remember to speak into the microphone when you're answering the questions. Thanks.
Estatica, Montgomery College. None of the models seem to take into account the impact of phages on the carbon cycle and how that would alter the export.
Yeah, we actually talked a lot about that at the meeting, and you'll see in the report there's quite a bit about phages, and in terms of blooms, the cause of the demise of blooms and production of all kinds of dissolved organic matter, and so yes. I'm glad you brought that up, because that didn't really come up yet today, but was something that came up as part of the priorities for future research. So, yeah.
I'm Mark Brzezinski, UC Santa Barbara. Hi guys. A question for everybody, I guess. When I read the report, it was quite interesting. I think you did a great job, and it seemed to be looking for novel extensions of the wiring diagram that we saw for, say, exports. New pathways we didn't understand very well, or maybe entirely new ones. My question, it's not just for you, but you're here, I could ask this of the exports people too. How do we make progress in understanding when these different kinds of food webs, or at least different pathways within them, arise? What forces a certain situation to come into being versus the consequence of it being there? Does that make sense? Because for the exports, I think from a constraint point of view, you start with a given ecosystem, and you look at the consequences of that structure for the export of carbon. But if you're going to write a model or something, you have to know what gives rise to that ecosystem, so you understand it's created here, but it's not created over there, different ones over here, different ones over there. How do we get to that predictive capability of an ecosystem structure?
I'll take a crack at it. I think it's a question of knowing the history of where things came from and where they're going, something you might call the trajectory. And so I think you can't know everything about, everything you see in the ocean and what its past history was, but I think a lot of the approaches, for example, that are based on Lagrangian tracking of water parcels can give you an understanding of the trajectory of the community and all of the processes that are going on in that community over the time that you're tracking it. And so I think that's a viable approach, but you sort of have to then piece together bits and pieces of those trajectories in order to really understand really to answer your question. Otherwise, it's what initiates the phytoplankton bloom, and you sort of have to be there in the dead of winter and measure everything all the time.
I think also this is part of what Cindy was referring to, that's part of the knowledge we do have. We do know a little bit of what causes flux events, a salt bloom or diatom bloom or a swarm of euphorsids. What we don't know is how important and how often these things happen and what the timing is, how fast it happens. So maybe looking at all 5 export pathways at the same time will give us a little bit better idea of how it relates within the whole thing.
So if I could just add one thing, is we actually had a discussion in the workshop of how could we identify either not traits of organisms, but traits of ecosystems that would lead to episodic export events or large flux events or generally periodic flux events. And so I think that's beginning to touch on what you're asking. And I think my own feeling is I think that's a very powerful way to go. I think it's very challenging, but I think it's a very powerful way to go. And I suspect that something along the lines of a Darwin-type approach, maybe not globally, but something of that kind of approach would be a start in that direction.
I'd like to, clearly, we now have the ability to recognize the kinds of particles that are sinking through the water column through imagery, and by combining different imaging modes, we can say, for example, we add a chlorophyll fluorescence function to the Carbon Flux Explorer, we could detect aggregated phytoplankton, fecal pellets, amorphous glop, as I showed. Actually, if all the animations of all the cruises that I described in my talk are online at Biogeosciences, and if you look at them, you see the structure of the large aggregates is either totally cohesive or obviously looked like it was an appendiclarian house, or it was just tapped with some stuff in it that fell and just sort of started to dissolve. So the whole thing is imaging allows you to tell how the biological carbon pump is working. And one of the challenges for us is, within a process study, there's no problem. And the other thing is to get a statistical outcome that might be useful for a food web model, or to address Phil Boyd's question. Supposing you took 10 profiling floats with optical sensors and imaging and everything Andrew wants, and let them go all at the same place. They all cross-calibrate their sensors, and then physics does the perturbation experiment, and you get so many different outcomes as they drift apart. And you will get the sort of correlation length scales that relate to remote sensing. And that could be and so you get an ensemble of observations of flux that then a modeler could then build a parameterization on.
So we have one online question, then I'm afraid we're going to have to cut this off so that we can get to the student talks. But I encourage everybody to read the report. I encourage everybody to, it's only short, it's very brief, about 25 pages, and then send emails and comments to Heather or myself, and they can get incorporated. So the online question?
Hi. So this is a question from Cheryl Harrison at NCAR. It's a question for Holly. It says, you mentioned the role of mixotrophs and carbon cycling as being a net source of carbon as opposed to a net sink due to their rapid recycling. Can you elaborate on this idea more, and in particular, why there may not be a mesozooplankton class grazing on the mixotrophs with the associated fecal pellet flux?
Right. So, I think, once again, this is a situation in which, or mixotroph primary production, and whether they're net fixers of carbon or respirers of carbon, is going to depend a bit on the context in which we're observing them. So while I would argue that there are going to be some scenarios in which they're very much functioning as key primary producers, I think there will be other scenarios, for example, if we think about warming oligotrophic gyres, in which they will potentially be functioning more as heterotrophs and more as respirers of fixed carbon. And I think in either case, understanding the traits that govern their palatability will be critical to understanding exactly how strong that flux to zooplankton size classes will be and the potential for export as fecal material. So not necessarily a very straightforward and global answer to that question, but again pointing us to the need for more work and identifying particular cases in which different ecosystem scenarios might be more likely than others.
Okay, so I think thank you to the speakers and the members of the organizing committee who braved the panel. And hand it back over to Heather.